Hello and welcome to video lecture number 13, which covers section 1.8, day 2, combinations of functions, applications. By the end of this lesson, you will be able to decompose two functions together, and you will also be able to model various situations using combinations of functions. Example 1 asks us to find two functions, f and g, such that h of x equals f of g of x. When we are asked to decompose functions, we are asked to do the exact opposite of what you've done in the previous lesson. We are not going to combine two functions, rather we're going to pull them apart from something that's already been combined. If h of x is the composition of f and g, notice that g of x must be the input function. So when we look at example 1a, I notice that in parentheses, there is x plus 1 showing up in both sets. Therefore, we can assume that g of x, the input function, must be x plus 1. Well, what was x plus 1 input into? Well, that was input into the function f of x. So if we write f of x as x squared minus 3x plus 4, and instead of x plus 1's, I just have single x's, you can see that we must have plugged g of x into both spots to create the composition. Moving on to example 1d, I notice that inside the absolute value, I see 3x minus 2. This appears to be the input function, so we will write g of x equals 3x minus 2, and what was that plugged into to create h of x? Well, we'll call the outline or outside function f of x, and that would simply be absolute value of x. You can check your work by verifying that if you were to plug in the input function g of x into f of x, what you end up with is the composite h of x. So here are our answers for example 1a and d. Please try b and c on your own and have them ready to check for tomorrow. Part 2 of this lesson and the remaining examples that follow give you an opportunity to see some application problems that involve combinations of functions. Please take a moment to read through example 2 by pausing the video. Notice you are given two functions, f of x, and you are given g of x, and we are asked to do two compositions. We will start with the composition f of g of x. F of g of x means we need to input x minus 5,000 into the function f of x. By doing that, we are left with 0.03 multiplied by x minus 5,000. In order to simplify this function, we could distribute, but I think in this case it's better to leave it as is. Now we will try g of f of x. So g of f of x can be thought of as plugging 0.03x into the function g. Although it's not explicitly stated, x in both of the functions represents the amount of weekly sales you have. If you consider that and the fact that we must sell over $5,000 to begin earning the 3% commission, that should be enough for you to be able to determine which equation makes sense. In the function g of f of x, notice we have 0.03 times x. Well, this implies that the 3% commission can be tacked on to any amount of sales x that you have. Well, that's not what the problem states. The problem states you must sell over $5,000 in order to get that 3% commission, and that's what the x minus 5,000 implies. X has to be greater than $5,000 for us to start making that 3%. Otherwise, x minus 5,000 is negative. So with that being said, f of g of x represents this situation. Moving on to example 5, We have a scenario that gives us three functions. It says let P of t be the total U.S. population t years after 2000. We have the function B of t, which represents the number of births in the U.S. t years after 2000. And we also have D of t, which represents the number of deaths in the U.S. t years after 2000. Part A is asking us to write a new function, call it C of t, which involves all three of the above functions, that is designed to represent the percent change in the population in any given year after 2000. First, I will start by showing you a verbal interpretation of the percent change. Well, in order to get a percent, we must have a fraction or a ratio of some sort. In the numerator, we must put the increase or decrease in the overall population in that given year. Well, since population has been going up in the United States every year for the last who knows how many years, we're going to just call it increase in population. When you compare that or divide it by the total population in that same year, that will give you the percent change. Now we will substitute the functions P, B, and D to actually describe that. Well, if there's going to be an increase in the population, the number of births must be greater than the number of deaths in a given year. So therefore, we will subtract number of deaths from the number of births and get some value, and then divide that by the total number of people in the U.S. Now we will substitute the function notations for those. So our function C of t, when using the other three functions, will look like C of t equals B of t minus D of t divided by P of t. So we have a difference of the two functions in the numerator, and then we also have a quotient of that divided by P of t. Part B asks you to interpret the value of C of 13. Well, now that we know the function C of t is the percent change, 13 is our t value. If you look above, t represents the years after 2000. So if it's 13 years after 2000, the year must be 2013. So this function would then represent the percent change in the U.S. population in that specific year, 2013. Please take a moment then to try examples 3 and 4 on your own and have them ready to check for tomorrow. So this concludes video lecture number 13. Please take a moment, as always, to look back over the video lecture and the notes you've taken to come up with at least one question you still have after completing the problems and watching the video. Thanks again for watching, and good luck.